There you go. Okay, so the question is, how do we calculate the torque? This is the torque. Caused by gravity. Now, the equation that we have seen for torque, or one of the equations that we have seen for torque, is that the torque is just the radial distance. So that's from the pivot point to your force times the perpendicular force that creates the perpendicular force to that radial line. Now, in the case of your arm, there's a couple of things like, what is this radial distance? I'm going to simplify my arm. Instead of doing an arm, I'm going to do a rectangle. So this is the model of my arm. And you can imagine that I can divide this arm in small segments. So I can have just little pieces of my arm. And I'm going to assume that each piece is exactly the same mass. They may not be necessarily the same size, but each one of them have the same mass. So each one of these little guys, I'm going to call it M1, M2, all the way to Mn. Each one of these guys, because they have their own mass, they're going to have their own pull caused by gravity. And for each segment, I'm going to have an R1. Well, I'm going to have a radial distance. So this is my pivot point. I'm going to have R1, I'm going to have R2, R3, which is going to be this, all the way to Rn. This is R1, R2, R3. So if I want to calculate the torque, well, I will have to do R1 times the force of 1, R2 times the force of 2, and so on until Rn the force of F. Yeah. Now, the number of segments, you can have a lot of segments. Like the smaller the segment that you're going to have, the more precise your results is going to be. The bigger your segment, well, the less accurate, but the faster you're going to do. So obviously, the way you do this basically is by using calculus, and you do an integral and you solve for the torque. Now there's an easier one, there's an easier way, but there's a way that we can work around this long summation without the need of calculus. And that's basically by defining what we call the center of gravity. Okay. And the center of gravity is a point in space where we're going to focus we're going to concentrate all the mass of the extended object. Okay. So So instead of calculating all these n number of torques or all these many torques, what I'm going to say is, okay, my arm has a mass m, and that mass is going to be concentrated in a single point. And then the torque is just going to be the distance to the center of gravity times the force times the perpendicular force. And this force is created by the whole mass. Okay. Okay. And so what we're going to try to do is, how do we calculate the center of gravity? Or how do we calculate the center of gravity? How do we calculate the position of that center of gravity? Okay. This can be applied to different situations. Like if you want to calculate the center of gravity of the human body, you can try to do this. We usually going to do it to calculate the center of gravity of how do you call it, for arms, legs, and stuff like that. Okay. Any questions? Okay. So let's imagine that we have two masses, and these two masses are connected by a small rock. So we're going to have a mass M1, and it's going to be connected to a mass M2. Okay, there's a distance D in between. And this rod over here, I'm going to ignore the mass of that rod. Okay. And I'm going to try to find out what is the location of the center of gravity of this configuration. And on that center of gravity, I'm going to put kind of like a pivot point. Now, one of the characteristics of the center of gravity is that if you put a pivot point at the center of gravity, the net torque is going to be equal to 0. Okay, so the net torque, when the net torque is equal to 0, the torque created by mass number 1, you can imagine that this mass is going to try to rotate in this direction. And this torque over here is going to try to rotate in the opposite direction. So at the center of gravity, the torque of these two cancel each other, and it's going to be in balance. Okay, so the way we say that something is in balance, we said, okay, the net torque is going to be equal to 0. There's no rotation. Okay, so that's a way to calculate, to figure out if you actually find the center of gravity, is by try to find the balance point. Okay, so we're going to try to find the center of gravity. So we're going to try to find this point over here. So the way I'm going to do it, or the way you start to do it, is that I'm going to, first of all, I'm going to set up a frame of reference. So I'm going to have my X and Y coordinate. This is going to be my origin. And I'm going to have the different positions. So I'm going to call this X1. This is going to be the position of the center of gravity. And this is going to be x2. Now, what I want to find out is where the net torque is equal to 0. So that basically means that the sum of the torque by mass number 1 plus the torque of mass number 2 together have to be equal to 0. And I'm going to try to find out what is that point x for the center of gravity. Okay. Now remember, the torque is the distance from the pivot point to the mass times the perpendicular force. Okay. Now, the distance between M1 and the center of gravity is going to be that position of the center of gravity, whatever it is, minus x1. And the force of gravity and the force, then the perpendicular force is whatever I have M1 times gravity. This is rotating counterclockwise, so it's going to be positive. So we're going to have a positive torque. Now for tau 2, the position R is going to be the position of x2 minus whatever that center of gravity is, times m2 times g. And this is going to be rotating clockwise, so we're going to have a negative torque. So we're going to have a negative here. Okay, so remember, we need to do tau 1 plus tau 2 equals 0. So that basically means xg minus x1 m1g minus x2 minus xcg m2g equals 0. Now from here, it's going to be a little bit of algebra. So if you get lost, just let me know. Send in the chat. Like if you cannot follow, just let me know and I'll go slower. So I'm going to expand this factor over here. Well, first of all, I'm going to divide the gravity from both sides of the equation. So I'm going to divide this and this. So and 0 over g is going to be 0. So I can get rid of the gravity. And now I'm going to expand these factors over here. So I'm going to have xcg times m1 minus x1 m1. And these will be minus x2 m2 plus xcg m2 equals 0. Now I want to solve for the position of the center of gravity. I want to solve for xcg. So every term that involves xcg, I'm going to leave it on this. I'm going to leave it on this left side of the equation, and everything else I'm going to put it on the right side of the equation. So here, I'm going to have xcg m1 plus xcg m2 equals x1 m1 plus x2 m2. Okay. Now I'm gonna factor x the center of gravity. So I'm gonna have the center of gravity m1 plus m2 equals x1 m1 plus x2 m2. And from here, I can solve for the center of gravity. It will be x1 m1 plus x2 m2 over m1 plus m2. Okay. Now, this is having two masses. What happens if we have 3 or 4 or 5 masses? Well, you will need to do something similar. You will have to do, if you have 3 masses, then tau 1 plus tau 2 plus tau 3 has to be equal to 0. If you have 4 masses, tau 1 times 2 times 3 times 4 equals to 0. Now, you will have to repeat this. And at the end, you're going to end up with an equation that is very similar to this one. And actually, you have more than, or you have an n number of masses, then the way you calculate the center of gravity is by using this equation. x1 m1 plus x2 m2 plus xn mn. N. Okay. If you have masses, for example, if you have a configuration that looks like this, so you have you have a distribution in x and y direction. So the center of gravity has to be in 2 dimensions. So you can apply something similar. So you can calculate the center of mass in the x direction. You can calculate the mass in the y direction. And the equations are pretty much the same. The only difference is that you're going to change the x coordinate for the y coordinate. So you will have y1 1 plus y2 2 plus yeah. Now, something that is not very obvious is that the center of mass or the center of gravity doesn't have to be in the object itself. Like if you look at this structure and you just look at these two, the center of gravity of this structure is going to be somewhere around here, depending on the masses and the value of the masses, but it's going to be somewhere there in between. And for M2 and M3, the center of gravity is going to be somewhere around here. So if you calculate the center of gravity of the 3-body structure, the center of gravity is going to be somewhere outside the structure. Okay, so the center of gravity doesn't have to be on the object. Now, if you have something like an arm, At the end is the example that we want to talk about. Well, for something that looks like an arm, or something that looks, you can imagine a disc or a sphere, the center of gravity is going to match with the geometric center of that object. So if you have an arm and you can approximate that arm with a rectangle, the center of gravity is going to be at the center of the rectangle. So if this has a length L, the center of gravity is going to be at L/2. And if this has a width W, then this is going to be W/2. If you have a sphere, you have a disk, the center of gravity is going to be right at the center. There are some figures that are a little more complicated, like if you have a triangle, then the center of gravity of this thing is at 1/3 of the height and 2/3 of the base. But usually, when we try to calculate the center of gravity of the human body, we usually can use rectangles and spheres and disks most of the time. Yeah. Now imagine that you have a donut. So if you imagine a donut, the center of gravity matches the geometric center. In that case, the geometric center is right there in the center of the hole. So again, this is another case in which the center of gravity doesn't have to be on the object. Okay. Have you seen the Olympic Games when they do the high jump? That is, they do this kind of weird shape that they run in, and you have the bar, and when they jump, they do like this really weird curve. So if you imagine this, a human body, the center of gravity of a person is usually around the belly button, is somewhere around there. Depending if you have more massive legs or an upper body strength or whatever, but it's usually somewhere around there. For babies, it's a little bit taller because they have a huge head, depending on their respect of their body. So the center of gravity is a little bit higher. But for grown-ups, it's usually around the belly button. Now, when you are standing, well, you're gonna have your center of gravity somewhere around here. But when they arc their body like that, then the center of gravity, and I'm gonna exaggerate here. The center of gravity is gonna be somewhere below the body, kind of like a donut. That's gonna be in the center. So if you cut the donut, the center of gravity is still gonna be there. Sorry. Okay. So why does that matter? Because the energy that you require to jump is going to depend on this center of gravity. So if you can lower this, then the energy that you require to jump over the bar is going to be a little bit lower than if you try to jump with the other technique. So it's just a little bit more efficient. Okay. But this is something that's very interesting on the human body, is that we can change the center of gravity just by modifying the position of our body. And the location of the center of gravity has to do a lot with the stability. So whether you are stable or unstable depends on where is your center of gravity with respect of a pivot point. So if you have someone working on a wire, they usually, the way you see it is that they have a huge bar, and that bar bends way, way, way below. So you have a bar, and the bar just extends a lot. Now, the idea with this bar is the same idea as the guy twisting the bag to jump. They try to lower the center of gravity below the pivot point. So on someone walking the wire, by having this huge bar, the center of gravity, instead of being on the belly button of a person, the center of gravity is going to be somewhere around here. Now, if you, and the pivot point is going to be on the feet. So by putting the center of gravity below the pivot point, so if this is my pivot point and I have my center of gravity below, the most stable position is when the center of gravity is exactly below the pivot point. This is kind of like a pendulum. So if you have a pendulum and you let this oscillate back and forth, eventually it's going to come to a rest. And it's going to come to a rest when the mass is below the pivot point. So this is the center of gravity below the pivot point. So this is a very stable position. That's basically what you try to do. If you have the opposite case, when you have the pivot point and you have the center of gravity above the pivot point, if they are exactly at the right position, they tend to be, they can be in balance. But if these things moves a little bit, then this is gonna be out of balance, and this is gonna be an unstable position. Okay. So that's basically what happens with babies. Like you have their feet, but the head is huge compared to their body. So the center of gravity is way, way high, and they have a lot of trouble trying to stand up because they cannot still control the center of gravity to be above their feet. So just a little bit of motion, they cannot control the motion of the head, and they just fall. Have you seen babies walking when they start walking and they just feel like it looks like it's always falling, and it's basically for that. Okay. Any questions? Everything makes sense? Ish? No? Quack?
It makes sense.
It makes sense? H?
Okay.
Okay. Do. Okay, so we're gonna do a small problem. This is the same bar that we've been talking about, that we've been using, for example, last couple of times. I'm going to assume that this bar has a mass m. And I'm going to have this mass is going to be 5 kilograms. Okay, and what I want to find out is what is the torque. Okay, I want to find out what is the torque at the pivot point, and the pivot point is going to be this guy over here. Okay, so the first thing that I need to do is to find out where is the center of gravity, because they're not giving me an applied force or anything like that. I need to find where is the center of gravity. Now, in this case, Lexi, how you doing? I haven't bothered you in a couple of weeks. I mean, a couple of days.
I know, it's sad.
It's kind of weird, right?
Yeah, I was missing being called out for.
There you go. So tell me, where is the center of gravity of this?
It's gonna be in the middle.
It's gonna be in the middle, okay? So it's gonna be right here in the middle. So if this is 1 meter, this is gonna be 50 centimeters. And because we are looking at the torque created by gravity on that mass, this is gonna be just right here. This is gonna be the weight. So to calculate the torque again is a distance times a perpendicular force. The distance that I need is the distance between the pivot point and where my force is. So this will be it's going to be 25 centimeters. I'm going to put it in meters times the perpendicular force. This is already at 90 degrees. So this is already my perpendicular force. So this will be 5 times 9.8. So I got 12.25 newtons meters. Is rotating clockwise. So this will be negative. Yes.
You got the 25 centimeters from the distance between the pivot point and the center of gravity, right?
Correct. Yeah. No, don't confuse with this 25. It's just between here and here. It's going to be 25 centimeters. Okay. Make sense? Okay. Do another one. Let's say that you have the arm. Oops. You have the arm of a person. The length of the arm is going to be 70 centimeters. And at the end, this person has a steel ball. Okay. This steel ball has a mass of 3 kilograms. And the mass of the arm, of the whole arm, I'm going to say that is 4 kilograms. Okay, and I'm going to assume that the arm is completely horizontal, is parallel to the ground. Okay, and what I want to find out is what is the torque with respect of the shoulder. Okay, so really quick, write down the forces that you have in this problem. Just write it down. Okay, Jacob, what forces you have? Noah?
I said the force of gravity
On where?
on like the arm of the boat.
Lexi?
The force of gravity on the arm and then the force from the weight of the ball.
Yeah, so maybe that's what you guys were referring, but yes, you have two forces. You're gonna have the force of gravity. You're gonna have the weight because of the ball, and you're also gonna have a force, the weight of the arm. So you have those two forces. Now, the force of the weight from the ball is gonna be just at the ball. Now, where is the weight of the arm? Mallory? Aubrey? Where is the center of gravity? So we need to find the center of gravity. It's gonna be at the center of gravity, and we need to find the center of gravity. So this arm, I can replace it for something like this, just a rectangle. And the ball is gonna be somewhere around here, and this rectangle is gonna have the same dimension, 70 centimeters. Right now, I only care about the X direction. I don't care about the Y direction. So in this rectangle with a length of 70 centimeters, Ian, where's gonna be the center of gravity? 35 is gonna be right at the center. It's gonna be right at the center of that rectangle. Okay, so my two forces, this is gonna be the weight of the arm, and this is gonna be the weight of the ball. Yeah, and my pivot point is gonna be somewhere around here on my shoulder. So this is the shoulder. Yeah, Aubrey, makes sense?
Yeah, so the weight of the arm, then you just disregard the weight of the ball, right?
No, we count in both.
Right, but
Yeah.
for finding the center of gravity, like you don't care about the weight of the ball then?
Correct.
Okay,
We're just looking at, this is just gonna be the 4 kilograms, and this is gonna be the 3 kilograms. Yeah, Paige? Makes sense? Okay, so now we can calculate that torque. So the torque is gonna be the torque created by the arm plus the torque created by the ball. Okay, now this is my pivot point. The arm is gonna try to rotate my arm clockwise, and the ball, the weight of the ball, is also gonna try to rotate my arm clockwise. So both of them create a negative torque. So we're gonna end up with a negative torque at the end. So try to calculate the torque really quick. Okay, so you're gonna have the torque created by the arm is gonna be 0.35 centimeters. We're gonna put it in, I'm sorry, 0.35 meters. And then the weight is gonna be the 4 kilograms times 9.8. That's gonna be negative. And the torque of the ball is gonna be 0.7 meters times 3 times 9.8. And this one is also gonna be negative. And at the end, I think you guys, yes,
Oh, why is the 0.35 negative?
It's going clockwise.
yeah, because it's going clockwise. So the torque is gonna be negative. Yeah. And at the end, I think you end up with minus 34 or something. Lexi,
Negative 34.3.
0.3 newtons meter. Yeah. Page, it's making sense.
Where did the 4 came from with the arm?
The 4 comes from the mass of the arm, and the 3 is the mass of the ball. Yeah, Jacob? Aubrey? Yeah. Okay. So now you're gonna do, this is gonna be on your own, it's the same arm. And it's holding exactly the same mass. So you have the mass of the arm to be 4 kilograms. The mass of the ball is going to be 3 kilograms. But now the arm is raised 30 degrees.
So it goes back as an apple, but the arms are right hand. Yeah, so you know, The same like 7 centimeters.
Oh, okay, so.
Yeah, yeah, the arm is 7 centimeters. It's the same arm as before. Uh, no, no, correct. Just try to find out where is the 30 degrees on your post.
I mean,
I think you got the 30, but just right wrong. So I want you to understand where this 30.
oh, Curry's angle.
Yeah, but you don't need the angle between the horizontal and the arm. The angle that makes this force rotate the arm from the back. So, yes, it's gonna be 30. But I want you to see where that 30 is. This. This up. Okay, so I'm gonna try to do it.
And there are two ways that you can try to do it. One is using the moment of arm, and the other one is using the perpendicular force. So I'm going to try to do the moment of arm for the ball, and I'm going to try to use the perpendicular force for the arm. Okay. So first thing, I'm going to simplify the model. So just going to look like this. And this angle is going to be 30 degrees. Okay. I'm going to be looking at the ball right now. So the force is going to be like this. Okay, and I need to find what is the perpendicular force, what is the perpendicular component of this force, perpendicular with respect of this radial axis. Okay, so I need to find out what is this perpendicular component. Yeah. Now, here I'm going to have 90 degrees, and if this is 30, this is going to be 60. Okay. And this over here is going to be 30 degrees too. So if I have the torque to be the radial distance and the perpendicular component of the force, the perpendicular component of this force to this axis is going to be, what is the mass? 3 kilograms times 9.8 sine of 60. So I think I got it wrong with you, Paige. And the distance is going to be 0.7 meters. And again, this is going to be negative because it's rotating clockwise. Okay. Now, for the torque on the arm, I know that this force is going to be at 0.35 meters from the pivot point. Okay, and now I'm going to be using the moment of arm. Now the moment of arm is going to be this distance over here. And now 2 is going to be the moment of arm times the force. So the moment of arm is this length over here. And that's basically the adjacent side to this angle. And the hypotenuse is going to be the 0.35 meters. So this will be 0.35 cosine of 30 times the force, which is going to be 4 times 9.8. This is going to give me negative 17.82. And this one, oops, it's going to give me negative 11.9. So the net torque will be negative 29.7 newtons meter. Okay, so it's a little bit lower than what we had when the arm was at perfectly parallel to the ground. Okay, makes sense? Okay. Well, that's all for today. And if you don't have any questions, then I'll see you guys on Wednesday. And good luck. Hopefully we're all healthy and we don't have to isolate for a couple of weeks.